What I'm going to say now will seem to have nothing to do with anything, but is actually very, very pertinent to countercurrent contact. So just watch me do this mundane thing. Here I've got a board. I'm going to try to erase it. And these are these dry erase markers which wipe off, and actually they don't wipe off very well. So I'm going to do a two-stage cleaning process. I've got these little towel papers with my cleaner. I'm going to start cleaning this off. Notice that for the first cleanup, am I starting with a clean sheet of paper? No. This is a towel paper that I've used before. It's got ink on it. It's dirty. So for the first cleaning, I'm just going to take this partly dirty paper and do the first wipe off of the board. And only now, after I've done the first cleaning, am I going to take a fresh sheet of this top quality towel paper, whatever brand it is, and do the final clean, the second clean. The point is that when I do the first cleaning, there's so much ink here that it would be a waste of, this was a fresh sheet of towel paper, this is a fresh sheet of towel paper. When you're doing the first cleaning, when something's really dirty, why would you bother using a pristine, clean sheet of towel paper to clean it? You can use a towel paper that's kind of dirty to clean it. The first cleaning, the cleaning cloth doesn't have to be great. I mean, have some dirt on it. It's only for the second cleaning that you want that clean sheet of towel paper. Interesting thought, which we'll come back to in countercurrent contact.
With that prologue about cleaning the whiteboard, let's look at an example of gas absorption. 1 mole of a contaminated gas stream, composition 90 mole% air, 10 mole% benzene, is contacted with 2.0 moles of an absorption oil in order to remove some of the benzene. That's a good thing, because I certainly wouldn't want to be breathing benzene. Determine the benzene mole fraction in the exiting gas stream for each of the 3 schemes indicated below. As usual, neglect any evaporation of oil as well as dissolution of air in the liquid. The equilibrium relation is Y is 2.5x. What are these 3 schemes? The scheme here, number 1, is just single stage absorption. We've done that before, but I don't mind reviewing it. Scheme number 2 is 2 stages. Notice that here we're using pristine clean, fresh oil to do the first cleanup, as well as using pristine clean, fresh oil to do the second cleanup. Scheme number 3 is what's called countercurrent contact. You'll notice that in doing the first cleanup of the air, we're not using pristine clean, fresh oil. This oil here actually already has some benzene in it because it absorbed some benzene in stage number 1. So this scheme here corresponds to what I was talking about in cleaning the blackboard. For the first cleanup of the gas, I don't really need a pristine clean piece of towel paper or a pristine clean oil. The comparison of all these 3 cases is fair in the sense that in all 3 cases I'm using 2 moles of oil. Here I'm using 2 moles of oil in a single stage process. Here I'm using 2 moles, 1 mole per stage, so the total is 2. Here all the oil comes in the top 2 moles, so it's a fair comparison. So scheme number 1, this is just single stage absorption. You'll notice that there's really only one unknown here. How many moles of benzene remain in the air after the absorption process? And by the definition of mole fraction, Y1 is benzene over pure air plus benzene. By mass balance, whatever benzene didn't come out up here has to have come out down here. So these moles are 0.1 minus n, and the definition of mole fraction of X1 is benzene over pure oil plus benzene. Just by writing these 2 expressions here, I've basically already incorporated mass balance. This is the equilibrium relationship. We know the equilibrium relationship. Y is 2.5x, so I just substitute those in there. This is one equation for n. It turns out you can simplify this to a quadratic equation. There's always 2 solutions of a quadratic equation, and you have to choose the correct answer, which in this case is the one with the plus sign. And by solving this equation, I get n equals 0.0538 moles of benzene remaining in the leaving air. And so then I go back and calculate this mole fraction is 0.0564. So by using 2 moles of oil in a single stage contact, how clean is the exiting gas? Well, the mole fraction of benzene has been reduced from 0.1 coming in to 0.0564 leaving. That's a review of single stage gas absorption. We've done this before. Scheme number 2. I have to start with stage number 2 because for stage number 1 I would need to know this outcome of the first absorption, and I don't know that. So yes, absolutely I'm going to start with stage number 2, the lower stage. Here I'm using the names N2 and N1 to indicate the moles of benzene that are in the air that came out of the lower stage, stage number 2, and the upper stage, stage number 1, very logical name. And I kind of repeat the calculation I did before, I just do it twice. So you'll notice for the lower stage, aside from the fact that this is called N2 now, and that the number of moles is 1 mole of oil, I'm basically doing what I did before. And so the equilibrium relationship is N2 over 0.9 plus N2, that's just Y2, is equal to 2.5 times X2. What is X2? Well, by a material balance, the number of moles of benzene in this liquid here is 0.1 minus N2. Solve the same kind of quadratic equation as we had here. I come to the conclusion that there's 0.0702 moles. N2 is 0.0702 moles of benzene left in the gas that's leaving stage number 2. This gas that's leaving stage number 2 is the input to stage number 1. So I do another single stage absorption process. This time the moles of benzene entering were 0.0702. Same kind of story. The moles of benzene here I call N1. So I again apply the equilibrium relationship. Y is 2.5 times X. Again solve a quadratic equation similar to this and come to the conclusion that N1 is 0.0491. So there's 0.0491 moles of benzene leaving the upper stage. And when I compute the mole fraction, I get 0.0517. So comparing these two cases, when I use the 2 moles in one stage, I got the mole fraction of benzene down to 0.0564. When I split the 1 mole into 2 stages, 1 mole of absorption oil each, I did better. The gas coming out of the upper stage is cleaner. The mole fraction is down to 0.0517. So 2 stages are better than 1. Now let's look at scheme number 3. Scheme number 3 is the equivalent of what I did with the whiteboard. As I said before, this oil here that is doing the cleanup in stage number 2, it actually is partly dirty. It has picked up some benzene. I can't do stage number 2 first and then stage number 1. In other words, I can't do this problem sequentially. These 2 stages are coupled together because I just don't know what's coming into stage number 2 yet. Let me write down the mass balances for stage number 1 and stage number 2. So for stage number 1, the moles of benzene that come in are 0 with the entering liquid, that's actually fresh oil, and the benzene that came into stage number 1 from stage number 2, the moles of benzene leaving are L-benzene number 1, which left stage number 1, and V-benzene number 1. In equals out, so this is this equation. If I now consider stage number 2, what's the moles of benzene that came in? Well, it was L-benzene here, and the 0.1 of the air that came into the whole process. And what's the benzene leaving? Well, it's the L-benzene 2 and V-benzene 2. So these are just my mass balances for the 2 individual stages. Then I just write down equilibrium for those 2 stages because for stage number 2, this stream and this stream are in equilibrium. They've had a chance to exchange solute, all that they want. And in stage number 1, this stream and this stream are in equilibrium. What's the equilibrium relationship? Y is 2.5x. So based on this mole number, V-benzene 1 over 0.9 plus V-benzene 1, that's Y1 is 2.5 X1. What's the mole fraction? Well, benzene over oil plus benzene. So that's equilibrium for this stage. Same kind of story for this stage. What's the mole fraction of benzene in the gas leaving this stage? Well, it's benzene V-benzene 2 over pure air 0.9 plus V-benzene 2. And that's 2.5 times X2, which is the benzene mole fraction in the liquid leaving the stage. So that's benzene over absorption oil plus benzene. So what has happened here is that I've written down both a mass balance equation for each stage and the equilibrium relationship for each stage. These 2 equilibrium relationships seem to contain 4 variables, but actually wherever I see L-benzenes, I can get them in terms of the V-benzenes. So these 2 equations ultimately amount to 2 equations and 2 unknowns. That's what I've written over here. So I've got two equations and two unknowns for V-benzene coming out of the upper stage and V-benzene coming out of the lower stage. I solve those equations. I'll show the MATLAB code in a minute. And out pops the answer when I solve these equations, two equations and two unknowns. So these are the mole numbers of benzene in this stream and this stream. What I'm most interested in is what is the benzene mole fraction in the final air leaving the upper absorption stage. And by the definition of mole fraction, Y1 comes out to be 0.0412, which is even lower. So the message here is that we've contemplated two ways of doing two stages. One of them is to use fresh oil coming in each stage, and the second one, which we just finished, is countercurrent contact. Countercurrent contact is better. You're using the same amount of oil, 2 moles, but you get a lower mole fraction of benzene in the final exiting gas. This is cleaner than it was with scheme number 2. So this is kind of a clear demonstration that countercurrent contact is best. And so from now on, we're just going to happily use that fact because we've proven it here. Countercurrent contact is best. So here's the MATLAB code. This is a little function. I call it F countercurrent because this is a countercurrent problem. Notice that I've got this nicely documented. I've said, F of 1, that's the left-hand side of what I called equation number 5, the first equation, and I want to set that equal to 0. F of 2 is the left-hand side of the second equation. I also want to set that equal to 0. And here I've got x of 1 and x of 2 nicely labeled. Those are the two benzene mole numbers. What were the two equations? I wanted this equals this or this minus this equals 0. Second equation, this equals this or this minus this equals 0. So if I set those two f's equal to 0, that's what I want to achieve. Here's the actual session that I typed into my MATLAB window. And MATLAB is great. It just has this function fsolve, as I've said before, which just automatically solves any equations. All you have to do is provide the function which evaluates the left-hand sides. And I called that countercurrent. So at countercurrent refers to that function. This pair is my initial guess for the mole numbers. I just made a really crude initial guess, saying that both those mole numbers were equal to the moles of benzene that came in, so that my initial guess is just a state where I had absorbed nothing, but that's good enough. So I just type this command, hit enter, and the equations are solved, and out pop these numbers. And so this is where I got the mole numbers of benzene. So that's how you use MATLAB to solve this problem. Kind of just for fun, or for my interest, what I've done here is taken scheme number 1, which was the single stage contact, and scheme number 3, which was the two-stage countercurrent contact, and I just wrote down the results for the mole fractions of benzene in the liquid phase and the gas phase above and below each stage, above and below each stage. So you'll notice for scheme number 1, this XY pair is this. This point here has this X and this Y, which are in equilibrium. This point here is the X and Y below this stage. You'll notice that there's an interesting step that forms. Similarly, for scheme number 3, this point here represents these conditions. This point here represents the conditions between the two stages, and this point here represents these conditions. And again, if I take this X and this Y, that represents this point, that represents the equilibrium for the streams, gas and liquid leaving stage number 1. This point here has this X and this Y, that's the vapor-liquid equilibrium here. So you notice again, there's this interesting kind of stair-step structure. That picture kind of makes you think, and in fact, this picture is going to figure prominently when we go further and analyze countercurrent gas absorption processes.